All right, hi, my name is Samavi, and today I'll be talking about safe and interactive crowd navigation. And this was also published in TRO in 2024. So in many service applications, robots need to navigate among pedestrians in order to accomplish their intended tasks. But as you can see in this delivery robot example, interactions with humans can be quite challenging. And to address this problem in a classical predict then plan approach, where the robot first forecasts human motion, then plans around it, the failure to account for the interactions between the robot and the humans can result in the robot getting stuck. As such, recent works focus on proactive approaches to close the loop between prediction and planning by modeling these interactions. And so this results in a game that needs to be approximated, and some methods do this approximation explicitly by explicitly modeling the interactions, while others, such as reinforcement learning approaches, do so implicitly. But what's common among these two groups of approaches is that they don't usually allow for safety constraints as they incorporate safety terms into the cost function rather than constraints. So in this work, we formulate and evaluate safe and interactive crowd navigation, or SICNav for short, a novel motion planning method for robot navigation in a crowd of multiple humans. SICNav jointly solves the prediction and motion planning problem by modeling humans to be following an optimal collision avoidance scheme called ORCA, which is commonly used to model humans in simulators, and then embedding that model as a lower level subproblem in a nonlinear model predictive controller that also has explicit safety constraints, resulting in a bi-level optimization problem that we reformulate and solve in receding horizon fashion. Our key insight in developing this approach was that many crowd navigation policies are trained in ORCA-based simulators and exhibit good interactive behavior. So we thought that if we incorporate ORCA directly into an MPC planner, then we can be at least as good while also allowing for explicit formulation of safety constraints. So here's the bi-level MPC problem, with the optimization variables being the states of all agents in the scene, which are positions and velocities, the actions of the robot, and the predicted actions of the humans in the scene. In terms of constraints, we have the following, but the most interesting is the one highlighted in red, enforcing that the humans in the scene are solving ORCA. And here's what that ORCA problem looks like. Details are in the paper, but the key points are that ORCA is itself a constrained optimization problem that solves for an optimal velocity for each human for one time step. And here's what the geometry of each ORCA problem looks like for the two gray humans illustrated. In this case, the objective is for the velocity to be in the direction the agent intends to go, illustrated by the gray dots in the velocity space graphs. And subject to a quadratic maximum velocity constraint, which is in blue with the feasible side shaded, and linear collision avoidance constraints, one per agent, which are in orange and green, and are derived using a velocity obstacle approach. We show in the paper that ORCA problems satisfy Slater's constraint qualification, meaning that the problem is optimal if and only if its KKT conditions are satisfied. And so with this useful property, we introduce a KKT reformulation to our bi-level problem, where we swap out the lower level problems and replace them with their KKT conditions. In the paper, we discuss the equivalence of solutions of the reformulation with solutions of the original problem, but I'm not going to go into details here. Maybe if we have time for questions, you can ask them. In simulation experiments, we evaluate SICNav in 500 randomly generated test scenarios in both an ORCA-based and a social forces model-based simulation environment with a doorway scenario like the videos on the left. The baselines include a predict then plan approach, which is just MPC with constant velocity motion predictions for the humans. And that you can see in the animations here. And we also compare to recent RL methods and a couple of reactive approaches. So you can see in these qualitative examples, the quantitative results are in the paper. I just don't like throwing a big table of numbers on slides. And so, but in these examples, you can see that the SICNav robot can kind of push the humans out of the way while the reactive or the predict then plan approach gets stuck, highlighting the interactiveness of our method. We also conduct real robot experiments where we ran a total of 80 runs over 5 scenarios with a varying number of humans. And all the scenarios resulted in this conflict zone in the middle of the room. And we compare SICNav with the predict then plan MPC constant velocity approach. We quantitatively show that SICNav performs better both in terms of efficiency as well as safety considerations. And we do qualitative evaluations as well. For example, in this video, humans break the assumption that they're following Orca and instead behave adversarially with respect to the robot. But because of the receding horizon nature of our approach, because we're replanning at 10 or 20 hertz, the method is able to kind of still get around them. And you'll see that happen in just a second. There we go. And so just a slight sneak peek, this work is from 2024. We do have follow-up work, one that uses a diffusion model to generate the intent for the humans that are then kind of refined with Orca in order to satisfy safety constraints. And that's been published in RAL about 6 months ago. And we've also deployed our method in the field completely with onboard sensing. And you can see that video here. And I think, yeah, presentation's shorter than minutes. So I think we have time for lots of questions.
Are there any questions? Please raise your hand. Yep.
Hi. So when you develop the real world experiments, you as a person like participating on the experiment, you were trying to reproduce the trajectory that Orca was saying that you had to follow?
No, we weren't.
Okay.
People were just walking. It's remarkably difficult to reproduce. You don't think about how you walk. This is not a conscious thing. And so, yeah, in my experience, it's remarkably difficult to, even if for like debugging purposes and trying to do a particular behavior, it's really hard to do it. It's really hard to stage.
Hi, a very interesting presentation. I'm just curious about how would you compare with these deep reinforcement learning methods that are available in the recent literature? That's the first question. Another question is how does your method scale up to multiple individuals that working in a very crowded session?
Yeah.
So
for the first question, I have a backup slide with the numbers in simulation. And so we compare with, SARL and RGL were at the time the most recent reinforcement learning methods for crowd navigation. And so we do beat them in terms of success rate, navigation time, collision frequency, I think, or at least we definitely have fewer collisions than them. And so we do that simulation analysis kind of quantitatively. And in terms of scaling, so we model interactively 5 humans. We can do it up to 5 humans while running at 10 hertz on the robot outside, like on that laptop. And we have an algorithm for choosing the most important and relevant humans. And 5 is a small robot. It's really hard to even, especially because the LiDAR is so low, to get more than 5 humans around the robot. There's just not enough space. But the other humans, in any case, if that does occur, we don't model them interactively in this way. We just model them for those humans. It's predict and plan. But since we're doing this at 10 hertz, yeah.
All right. Thanks.
Very nice presentation.
Thank you.
Will your method still work if we replace all the humans with the robots, optimizing the same formulation?
So that's an interesting question. Actually, I'm supervising a student doing that right now. But I mean, it wouldn't make sense, I think, to do that because the other robots, you know what the other robots are doing, or the operation that they're doing. I think what's the purpose of this work is to be able to model humans, which you don't know their behavior.
Cool.
Yeah, awesome work. When you're, I think I missed when you guys are modeling the humans doing deconfliction based on Orca. So in Orca, you assume that everybody's doing Orca together. So when you're solving the humans deconfliction, are you assuming that's like the robot's also working with Orca or independent of that?
Exactly. So the model of the humans assumes that the robot is also doing Orca.
Okay.
Yeah.
Thanks.
Just to make sure, is there a fifth speaker here present, maybe? If not, we can have more questions.
Or maybe he can go again, the previous speaker. Yeah, I was asking about the perception of the people because I guess you were using a mocap system or like
in this paper, yeah, it's mocap.
Okay.
So in this paper, they wore hats with Vicon system, but since in these videos you can see the onboard sensing. So on the top you see LiDAR.
Yeah.
And we just run YOLO on these images produced by the LiDAR. So those are actually those images you see on the top. It's not from a camera. These are actually from Ouster LiDARs. Like they can form this image that's actively collected. And we just, it's off the shelf YOLO, trained on Coco, and it works decently well to detect the humans. And then, yeah, we then get the depth position, 3D, well, bird's eye view position of the humans very easily that way.
Mm-hmm. But for the real experiments of SICNav, it was just
for the TRO paper, yeah, this was in 2024, and yeah, it was in the motion capture environment.
Hi. So for other dynamic obstacles, like let's say cycles on the street, right? Would Orca still be a reasonable model to assume?
So I think Orca, what's key about Orca is that it's dependent on this on several parameters. The most important of which being the intended direction the human needs to go, and then also the maximum velocity it can have, and how risk averse it is with respect to avoiding collisions. So that affects where that where those linear constraints for collision avoidance end up being. And so I think with different parameterizations, you can end up with a remarkably large number of variations. That being said, it can be difficult because you're solving in the, yeah, these render incorrectly in Windows, but because you're solving in this velocity space, it's really hard to have non-holonomic dynamics constraints in the program. So what you're seeing here is these like red constraints. So this doesn't render properly because on Windows, but imagine these sides are feasible. These kind of simulate maximum acceleration and unicycle constraints, which we actually use for something else. But you could do something like this for bicycles, but that's kind of out of the scope of what we're doing right now.
Right. Thank you.
Any other questions? Yep.
Excuse me, I have a question about just this slide, because you mentioned your follow-up work for using the different model to make predictions.
Mm-hmm.
Could you please introduce a little bit more?
Sure.
And my intuition is that for diffusion, maybe it's not very efficient. So for the real-time interaction, how do you deal with such a problem? Thanks.
Yeah. So that's a good question. And I have some more backup slides for this, I think. Yeah, so what this method does is that we use this particle filter inspired approach to take we we take the output, we take samples from the diffusion model. So running inference is actually pretty fast with this diffusion model. It takes about 0.05 seconds. We then use those. So for the first time step in there, we just take an average. So we use these models to, and again, sorry, this doesn't render properly on Windows, these slides, because they're vector graphics and gets rasterized in really poor quality. Yeah, so we take an average, a weighted average with all the samples being equally weighted for the first time step in the horizon. And then we run Orca one step forward, right, in the MPC. And then we see, because of the collision avoidance constraints, where the human ends up. And then based on the samples we have for that time step from the diffusion model, we can see, we kind of use those as measurements in a particle filter sense and say that, so these particles should be weighted more than the particles that the robot didn't go into. And so this way, we just go forward step by step, and we end up rejecting one of the modes that's incompatible with the robot's plan. So here the robot's going right, and so we end up rejecting the trajectory samples that have the human going towards the robot. So in this way, we kind of introduce a heuristic method to select one of the modes of the predictions of the human. And so you have to, at some point, when you're doing control, if you have a probabilistic distribution, you have to choose one action to take with the robot. And so this is so usually the choice is to take the action that is best in expectation, which might not necessarily be the best option when you have multimodal futures.
Cool talk. My sense is that when humans are in a large crowd, we are both doing sort of trajectory prediction, like but also there are a lot of social cues, right? And some of that is just in motion, but a lot of it is in body posture and facial expression.
Exactly.
And animals, I think, pick up on that as well. Yes. I think we all have the perception of, pigeons and cats and dogs are all very good at negotiating, but they do it differently because I think they communicate with human social cues at different levels, right? And I'm leading up to a question, not just a random comment here. This model, as best as I can tell, is representing human intention as trajectory, inference, and then conflict, possible conflict, right? Do you think a model like this, assuming if it was fed the proper features, if it was getting body posture, if it was getting facial expression, could learn social cues, or a model like this, just by adding, or do you think we need a different type of model that are trained in the semantics of social cues, if you wanted a model, a robot that was more naturalistic in its motion?
Yeah, so actually there is some work in the field of just open loop motion prediction. So that's actually quite a big field in robotics, where there's these data sets and you just try to predict the future time series of the trajectories. There's one paper from TUM actually, where there is that you use skeletons of the humans as an additional input in addition to history to doing this open loop prediction, and they do end up performing better in predicting the future. And so I think that's totally expected, because a moment before you start walking, you maybe lean towards, you shift your weight, that makes your skeleton kind of shift. And so I think those are very valid things to pay attention to. And then there's the jointness component of like the group behavior, depending on the relative positions, does affect each other. But that could also be relevant for sure. And that's why jointly predicting. So in this follow-up work, we actually propose the diffusion method. We extend an existing one to jointly predict all the humans in the scene rather than individually predict the separate humans. We end up performing better because we're doing it jointly. And so that does kind of, I guess that provides some evidence that this dynamic, this multi-agent dynamic is present in the data somehow.
Any last questions? If not, let's thank our speaker, and this closes out our session. Thank you.
Thanks.